This tutorial is designed to help you guys understand exactly what is going on when we talk about hybridization, as well as to understand what hybridization state a certain molecule or atom, usually carbon, is in. So hybridization is trying to reconcile these orbitals that we talked about in quantum mechanics to bonding and bond angles. So if we think about orbitals, right, or especially if we think about carbon, right, so carbon is going to have s and p orbitals. So here it's going to have an s orbital, and in addition to the s orbital, it's going to have 3 p orbitals. So we can have one, so maybe this is pz going straight up, and you can have one coming in and out, not in and out, so this sort of perpendicular angle here, right, maybe this is px, and then there'll be one coming straight up and straight down, maybe this is py. And so in hybridization, all of these orbitals are mixed together to make hybrid orbitals. And so the way that's going to look, we could take something like this, and so these orbitals here are meant to be one coming straight out of the plane and one going back into the plane, as well as having 2 extra ones here on the side. And so for this, it's kind of hard to see, but what you can just imagine is what it would look like if you tied 4 balloons together. And also what you should be able to hopefully notice is this is starting to look very much like our tetrahedral carbon, right? So if we have CH4, carbon bonded to 4 things, it adopts this tetrahedral geometry, which is essentially what we have going on here. So this carbon is making 4 single bonds. We can also call these single bonds sigma bonds, and it's come from these 4 hybrid orbitals in the direction that these bonds are pointing. And so in this case, we have 1 s orbital, and all 3 p orbitals are hybridizing to make sp3 hybrid orbitals. But we don't have to have sp3 hybrid orbitals. We can have sp2 hybrid orbitals. So what does that look like? So instead of all of the bonds, all of the orbitals hybridizing, only 3 of them do. So we can draw our 3 hybrid orbitals like this, and then we have 1 left over. So here, say we have our 1 p orbital left over, and that's going to be perpendicular to all of our hybrid orbitals. Now, what kind of molecules will have hybrid orbitals or non-hybridized p orbitals, and how can you tell? Well, non-hybridized p orbitals participate in double bonds. So let's look at that. So we can imagine here a carbon, right? And the carbon is going to have one of its hybridized sp2 orbitals pointing this way, and it can be bonding to an oxygen. Oops, I'm going to make that a little bit smaller. That has one of its sp2 orbitals also pointed this way. Now, the carbon and the oxygen will each have 2 more sp2 hybrid orbitals that are pointing in and out of the page, but I'm not going to draw those for sake of clarity. Now, they both also have unhybridized p orbitals, right? And those are perpendicular to the plane of bonding. Now, when you bring these 2 together, what they can do is form these pi bonds. And they have these sort of extended shapes because they're sort of the sum of 2 p bonds, or p orbitals, sorry. So we have pi bonds here, and this is just 1 pi bond. And then again, this first bond, this original bond between them, the hybrid orbitals, is a sigma bond. And so the way we would look at that, right, this pi bond is essentially a double bond. So if we were to have a molecule like this, formaldehyde, right, this molecule has 3 sigma bonds, and it has this 1 additional pi bond. And since it has 1 pi bond, we know that 1 p orbital is not participating in the hybridization. And we have an sp2 hybridized carbon here. Okay, well, then the last case, what if we leave out 2 p orbitals? Well, we can do that as well. So here we'll have 2 hybrid orbitals. So in this case, we'll have sp hybrid orbitals. And they'll be going in the same direction, and then we'll have 2 unhybridized p orbitals, and they'll both be perpendicular to the hybrid sp orbitals, looking like this. So if we're to think about molecules that have this, right, so now instead of having 1 pi bond, we'll now need molecules or atoms that have 2 pi bonds. So one example of that can be acetylene, right? So a triple bond between 2 carbons, that has 2 additional pi bonds into the sigma bond. But another example that's equally sp hybridized is carbon dioxide. So here, the carbon is making 2 sigma bonds to oxygen and 2 pi bonds. They just happen to be 2 different oxygens. But it's still sp hybridized. And if we wanted to look exactly at what is going on here and what these molecules, what these orbitals would look like, we can do that. So let's first consider the acetylene, the triple bond case. So we have a carbon that has 1 sp hybridized orbital that's bonded to the other carbon. Now, of course, both of these carbons are also, their other sp hybrid orbitals bonded to hydrogen. And they have 1 pi bond that's coming from these 2 p orbitals from each of them, these blue ones that are going to be parallel. But there's also another dimension, right? They also have p orbitals that are going in this direction, that are unhybridized. And so this together, right, we have 1 sigma bond and these 2 unhybridized, p orbitals for 2 pi bonds, right? That gives us this triple bond that we saw above. What about carbon dioxide? What does that look like? Well, here we have a carbon, right? And the carbon has 2 sp2 or sp hybrid orbitals going with oxygen. The oxygen has its corresponding hybrid orbitals. So these two sigma bonds between the carbons and the 2 oxygens. And now a carbon in one of the oxygen, right, has the pi bond in this direction. However, the other carbon in the other oxygen has to have the pi bond in the perpendicular direction because it's the remaining p orbital. And so the takeaway from this, right, is how do we determine easily the hybridization state of atoms? And it's again to look at how many double bonds they have. So, for example, CH4 has 0 double bonds, therefore all of its bonds are sigma bonds, and it's sp3 hybridized. Whereas our formaldehyde has 1 double bond, so it has 3 sigma bonds and 1 pi bond, and is sp2 hybridized. Whereas our acetylene has 2 sigma bonds and 2 pi bonds, so it's sp hybridized. So I hope that helps you sort of visualize what's going on with hybridization.